Welcome to Week 9. This is the first lecture in Week 9, or Lecture 9A. We're going to be continuing our mechanical considerations. This week what we're going to do is we're going to look at a couple of issues having to do with steam. First of all, steam. It's used for two main reasons. Now there's a lot of other reasons that it can be used, but there's two crucial reasons. The first one is, for some reason, I have a minimal space for mechanical systems. And in this instance, think ships. Ships, everything, space is a premium. So trying to find ways to get heat to transfer, everything else is a premium. So steam is one way that I can carry a lot of BTUs in a real confined area. So minimal space. The second thing is complexes or districts where I have a lot of buildings or I have to travel long distances. Steam, again, is another way that as long as I can keep it in steam form, I can transfer a lot of energy over long distances, again, in a small space. Now, because of the great number of BTUs per pound when failures occur, it can be costly. So before we move on, what I want to do is take just a quick look at a steam table. Here we have a saturated steam table. Now these tables I included at the end of your lecture notes. Across the top we have the gauge pressure that we're looking at, so we're dealing with PSIG. We have the temperature that they're considering. We're looking at the specific volume that it takes up at that particular temperature and pressure. And over here we have the energy content. The first column, the saturated liquid, is the number of BTUs it took to actually at that temperature and going to that pressure going to that temperature, the number of BTUs it took to get the liquid to the point where it would boil. So if we go down at 0 PSIG, which is atmospheric pressure at sea level, our boiling point is 212. This is the volume it takes up, and it takes 180 BTUs, or 1 BTU per pound per degree Fahrenheit, to get water the minute it starts at a liquid all the way up to the point it's boiling. So that's the first column. The next column is the number of BTUs it takes to fully convert 1 pound of water into 1 pound of steam, in this case 970. The final column is a combination of two, to get water from the point where it's first liquid all the way up to it's fully vaporized is a total of this column plus this column, or 1,150 BTUs, and this is again in per pound basis. The next thing to know is steam is a demand-driven system. As long as there's a demand, steam will be delivered to meet that demand. Now, of course, this is also based on sizing, if the sizing permits. In other words, I have a large enough boiler. No mechanical force is needed on the supply side. In other words, steam has pressure. So the minute I have a requirement for steam, or there's a pressure loss, it's replaced. So I don't need mechanical force. I don't need pumps on a supply side. In fact, that's sort of a running joke around here. Steam must not be allowed to condense in unwanted areas, such as in the piping. So proper insulation and installation takes care of this. So insulation keeps the temperature up. Proper installation means that anytime I get a little bit of condensing happening because of the pitch of the piping, the condensate runs to a place where it can be eliminated. Speaking of condensate elimination, we have a special device in steam systems called steam traps They're used in various areas in a steam system, either to allow condensate a way to leave an unwanted area, such as piping, or to force steam to condense where we want it, like such as the discharge of a heating coil or a heat exchanger. Traps prevent steam from getting into the condensate return, so it's a way of separating. We don't want steam to race through and end up in the condensate piping. There's 3 real key locations for traps. This by far isn't the only location, but 3 key locations. The first one is we'll have steam traps located at various points along the supply line to keep what little condensate might happen in the steam line from accumulating. This is particularly true just prior to a pressure reducing valve. So just before a pressure reducing valve on the supply side, they'll typically put a trap. It's a place where you get some condensate, and it's a way to get the condensate out of the lines, out of the supply lines. The next one is at the exit of heat exchangers. This forces the steam to condense at a location of our choice. So any type of steam heating coil, heat exchanger, anything where we're dealing with where we want that steam to convert, go back through its latent change and give it up its BTUs, we need a steam trap on the discharge side. This blocks the steam from racing through the coil. It forces the steam to be there and go through its conversion where we want it to convert. And then finally, at low points in the delivery system, such as drop downs to control devices. So if I'm running steam lines high overhead in a mechanical room, I drop down to feed a device, let's say a steam humidifier. The steam is going to run into a control device first to regulate the steam into the humidifier. There's going to be times where I'm not using the humidifier over long periods of time. If it's a long down drop, then what steam is left in there will have a tendency to condense. That condensate will lay against the control valve and ultimately cause the control valve to fail. This is because condensate is real caustic. So there is a high failure rate of devices that are dealing with condensate. So that can be traps, control valves, condensate pumps, etc. Now, once we've had the steam go through a conversion, convert to condensate, there's several things that can happen with the condensate, depending on the system type. The first or most obvious one is the condensate is returned to the boiler. The second, maybe not so obvious, is the condensate is thrown away. It's simply pitched. Now, if the condensate is tossed, typically, the heat must be extracted first. And there's 3 typical uses for heat from the condensate. We can use that hot condensate to preheat makeup water. In other words, preheat the water that's going to make up the water at the boiler. We can use the hot condensate to preheat domestic hot water, or actually if it's hot enough or the usage is low enough, it can actually do the full heating of the domestic hot water. Or last of all, in colder climates, we can run the hot condensate and use it as a snow melt situation. Now again, most jurisdictions or by code do not allow hot condensate simply to pitch to the environment because of the adverse effect of that overly hot water to the environment. So here in Michigan, you have to drop the hot condensate below a certain temperature before they allow you to discharge it, and this is the reason that this hot condensate is run through these different mechanisms to dissipate heat. Now, the reason here in Michigan, or at least in Grand Rapids, Michigan, the condensate is thrown away is the source of the steam is so far away. Somebody's decided that it was a lot cheaper just to have everybody using the steam to pitch the condensate and use constant makeup water in the boiler. So again, it's the boiler used for the district steam in Grand Rapids, Michigan. The waste heat boiler is so far away that they're not returning the condensate. And again, the heat has to be dissipated out of the condensate prior to pitching. Now, condensate returns, if we are returning the condensate back to the boiler, because now we're dealing with a liquid, we don't have that pressure involved anymore, and usually I need some sort of pump to get the condensate back to the boiler. Now, there are some older gravity returns in real small systems, but large systems usually need some sort of pump to get the condensate back to the boiler. Again, because of the caustic nature of condensate, these pumps have a high failure rate. Now, condensate in some areas actually have a sump pit where the condensate flows into, and there's usually a pump and then another backup pump. If both pumps end up failing, there's an overflow which causes the hot condensate to spill out, so you don't have a flooding situation. So here's another thing that, again, because of the caustic nature of condensate, there's a high failure rate in devices that are associated with the condensate. Of course, one of these is steam traps. The most common energy concern in the steam system. Again, steam traps are located in a number of different areas. A considerable amount of heat can be lost from a failed trap. So if traps fail, typically they fail open, so they actually allow steam to pass through. So we have steam that gets into the condensate lines, then it condenses somewhere where we didn't want it to condense. Now again, because steam is a load-driven item, for all the steam that I lose through, if the boiler's large enough, it'll simply keep replacing that steam into the coil, and I'll still get some energy out for what I want to do, but I'm losing a bunch of it into the condensate line. Now, the variables that influence cost, in other words, the cost of what this leaky trap is doing to me, is the steam trap orifice size. In other words, how big is the orifice or hole inside the trap, the steam pressure, and if I'm dealing with cost, now I need to know the hours of operation of the system and the cost of steam or steam production. So in this case, to calculate energy savings due to replacing or fixing leaky steam traps, I actually have two different situations that I have to worry about. So the first equation is if I'm purchasing district steam. In other words, I do not have my own boiler system. I'm not making up my own steam. I'm actually purchasing it from either a municipality or a private producer, whatever. I'm not producing it on site. I'm purchasing it. So the following equation is located at the bottom of this slide. So I'm looking at dollars per year. So the first thing I need to know is I need to know my steam loss in pounds per hour times the operating hours per year of whatever the device is where the steam trap is located. And then I need to know what I'm paying per dollars per pound of steam. So those are the variables that I need. The second situation is if I am producing in-house steam. In other words, I have my own boilers. Now, if this is the case, to calculate the dollars per year that I'm going to save by repairing a trap, again, I need to know my steam loss in pounds per hour. I need to know, again, the operating hours per year of the device where the trap's located. I need to know the BTUs per pound of steam, so I can go to a steam table and look that up based on the pressure of the steam I'm running at the facility. I need to know the dollars, the cost of my fuel, so if I'm making steam with natural gas, it's going to be cost per CCF or cost per therm or cost per MCF. I divide all this by my boiler efficiency and the number of BTUs located in that fuel type. So it happens to be therm, it's going to be 100,000 BTUs per therm. Now, how do I find out the pounds per hour loss? What we have here, and it's located also in your lecture notes, is a steam trap loss table. And you'll notice along the left-hand column, I have orifice diameters. Remember how I said that orifice diameter was one of several variables that I said we needed to calculate, in that case, cost. In this case, I'm just trying to get an initial step in actual steam loss. So I need the orifice diameter, left-hand column, and then I need to know the steam pressure I'm running. So that's across the top. So if I have a 1/8 inch diameter orifice inside the trap, and I'm running 100 psig steam, I drop down. For every hour, I'm losing 52.8 pounds of steam. 52.8 pounds of steam. So it's 100 psig, 1/8 inch orifice on my trap, and that's what I get. Now, there's these steam trap loss tables. In this day and age, there's apps to do it. You can go online to like Armstrong Steam or a number of different companies that sell steam traps. They have calculators online that can calculate this. So there's a number of ways of getting this information. So steam trap loss example given. I have district steam, which I'm purchasing at $18 per 1,000 pound of steam, and I'm using this steam for 4,380 hours a year. The offending trap has a 5/32 inch orifice in it, and the steam pressure that I'm running from this district steam is 100 psig. So the first thing I have to do is get that pounds per hour. So I go to a steam trap loss table, 5/32, orifice size at 100 psig. It turns out I'm losing 82.05 BTUs per pound per hour. Now I can plug in all the values in my equation, the pounds per hour lost, and actually that should just be pounds per hour, sorry. Anyway, the hours per year times the dollars per pound of steam, and I get my savings. So again, this should be pounds per hour. In my other example, I still have the same 4,380 hours of operation per year. This time I'm making my own steam. I have a boiler efficiency at 78%. I'm purchasing natural gas at $1.69 a therm. Again, the orifice is 5/32. My steam pressure is still 100 psig, and that's 880 BTUs per pound if I go to the steam table and look it up. From the trap loss table, I'm still losing that 82.05, and that should be pounds per hour. And I plug it into the equation, and I get the $6,852, $16 per year. This ends Lecture 9A, and when you're ready, you can proceed to Lecture 9B.